In previous videos, I talked about standing waves and vibrational modes. Vibrational modes are standing wave forms that the system really likes. They consist of resonant conditions where you get a very large output for a small input. Let's look at an arbitrary response of a spring that's fixed on both ends. In this problem, the vibrational modes are those for a fixed string. The first three vibrational modes for a fixed string look like this. The displacement is 0 at both ends, and it's sinusoidal between those endpoints. There are an infinite number of modes corresponding to increasingly higher frequencies and shorter wavelengths. A common vibrational analysis approach is to represent an arbitrary vibration as a superposition of these individual mode shapes. In this approach, we adjust the amplitude and timing of each individual mode and then just add up all of those contributions to get the actual string vibration. For our example, we'll use the case of a plucked string. The string, shown in blue, is fixed at both ends. We're going to grab the string 1/3 of the way down its length and stretch that point vertically so that the string forms this shape. Then we'll release the string. Our goal will be to mathematically determine the vibrations the string undergoes after we release it. This response is called a natural response, in which there's no input to the system. I'm applying what is called an initial condition by stretching it into this shape. Then I release the string and let it respond naturally. For example, if I pluck one side of this slinky, I get a vibration response that looks like this. This response consists of contributions from all of the vibrational modes of the slinky. Mathematically, the string's displacement as a function of time and position is this nasty equation. The sine n pi x term here is just our mode shapes. The natural response is always a sum of scaled versions of the mode shapes. The scaling of the individual modes is this term. The first 5 contributions in this summation are shown here for time t equals 0. The blue line is for n equals 1. It has the same shape as the first mode of the string. The green line is the second mode, the red is the third, purple is the fourth, and so on. If I add up all of these contributions, I get an approximation to the string's shape at time t equals 0. This sort of looks like the original shape. This point is rounded off, and we have a little wave here and here where it should be straight, but the resemblance isn't too bad considering we're only using a few terms. Finally, this cosine term here lets this wave oscillate up and down with time. Now I'll use MATLAB to simulate the behavior of the string based on our previous mathematical expression. I'm using 50 terms in the summation to do this animation. That looks pretty darn good. It's almost exactly what we saw in our earlier demo. The vibration of any system will depend on that system's modes. In fact, the vibration of interacting systems will depend upon the modes of the individual systems. This string has a vibrational mode, but the sound that we hear is the result of that mode interacting with the acoustic modes inside the guitar cavity and the wood forming that cavity.